Yeah, we can see the screen.
Oh, you can see it? Perfect, perfect.
Yeah.
So, all right. First of all, before we talk about the main content of this day, please, everybody, me and Elreza, we would love this session to be as interactive as possible. So if you have any questions at any time in this workshop, please use the chat line on Zoom to share your comments or your questions. If there are any areas that you would like us to spend more time on, if there are any specific questions that you have where you think it would be a good tangent for us to speak over, please do let us know, and we would love to adjust and gear back our agenda to make sure that the materials that we cover here like perfectly suits your questions and is 100% useful for you guys as well. All right, so let's jump into the agenda. So it is very important to understand the key point and objective of this workshop. So here we are ready to talk about some of the fundamental and also advanced topics in natural language processing, which is one of the oldest areas of artificial intelligence, if you will. So it's very important to understand where this topic sits across several and important and significantly popular area of data science these days. So we thought it's a good idea to just align our way of thinking about data science and specifically on how we should treat like big data problems in general and NLP specifically. And then we will transition of how we should actualize values from NLP. So if there are folks over this workshop that are interested to learn more about the theoretical aspects of like specific algorithms behind the scene, me and Elreza are more than happy to talk about like different resources, like some MOOCs, like massive open online courseware, some articles where you can get deeper on these topics. But in this session, it's very important to just gain some high-level understanding about like different topics, as I said, across some core fundamental areas of NLP and all the way to more advanced and cutting-edge technologies where it's being used by some very cool startups and also some big tech giants like Google's, Facebook's, Apple's of the world. So for that, let's align our thinking. Like when we talk about big data, what exactly are we talking about? Like this notion, I mean, all of us, we have heard about this term like a zillion times, but it's important to have a clear and crisp understanding. Like when I say big data, what exactly do we mean? So to some folks, when the data is larger than what their hardware can handle, they call it big data. And here we store some of these statistics, which are very old, like the process, the amount of data that Google or Facebook or eBay used to process about more than 10 years ago was substantially large. And now you can imagine that you should multiply that by a couple of orders of magnitude if you want to understand like how much data is being generated and stored by these giants in the world. And also, it's very important to understand that, okay, we have some big players in the industry. At the same time, there are really, really big institutions, like research institutions that are famous for producing like large data sets. And for all of these institutions, after let's say 2005, 2006, the term big data became very popular when they realized that, hey, this is some area that they can tap into and they can make real money out of this. And if you look at the left side of the screen, there are several, and this is just naming a handful of industries, some of the high-level data sources, like industries where contribute the most in producing data. And so I can share a very personal experience. So I do have a friend who's working with one of the largest research institute of physics in Chicago area. And he was telling me about this experiment that they're running right now, where they're collecting 1 terabyte of data per second. So just think about the hardware or the technology that you need to store that amount of data. And even if you can't handle that data, whether it's on-prem or on cloud, there needs to be a very well thought process for retrieve that data. And then you have to think about like okay, now we have the data. How do you want to actually process it? What sort of modeling you should put in place to go after data and uncover some insights from that data? And okay, so let's think about that for a second. When we think about like different sources or different industries that are producing data, what does it mean for us? And specifically, when we think about this workshop, a big chunk of that data is textual data. And when we talked about this area maybe 10 years ago, or maybe more than that, when people talked about textual data, it was only things that were typed out, like in HTML or something like that. But with the advances that's performed in OCRs, even things that they used to be stored as images or PDF files, now they can be easily extracted as text, and it's huge these days. And now companies are understanding that, all right, that can be a great opportunity to understand what is really happening inside their organization and outside, and tie their strategic decision making according to that. So let's understand why, like what happened, what is going on out there that the data production has become so easy. So first of all, generating data has become super cheap. So everything is smart these days. We are talking about like smartphones, smart gadgets, smart TV, smart vacuums, smart homes, and the interconnectivity among all these devices is becoming the Internet of Things. It's great opportunities that can uncover some of the very interesting aspects, which typically is not readily available across just one device. So things being connected that can open lots of new doors. And also the storage, the technologies for storing this amount of data, that also has become really cheap. So companies like Google and Amazon and Facebooks of the world, they invested a lot of money to make sure that data storage is cheap. And also they provided some platforms for both storing, retrieving, analyzing, and building some data products based off that, like on AWS, Microsoft Azure, Google Cloud. So, and also, for example, Databricks, they have provided a fantastic environment for running some big data analytics solutioning using Spark. So it's important to understand that people who didn't sort of contribute to producing data maybe 20 years ago. For example, my grandmother, she had absolutely no influence in producing data 15 years ago, but now she has a tablet, and I think she's responsible for, I think, at least 15% of the data on Instagram and Pinterest herself. So that's very common, and I know that we all can relate to that. And so, okay, based off that, let's think about it. People say data analytics is important. Data analytics is key. Most of universities, they have opened up their data science programs, mastered. Some of the people that I'm sure you all know, they have transitioned from some majors that were totally irrelevant to data analytics. They're coming to data science market, and there's a reason for that. And what everybody says is that data is good. But let's remember that there is a very important and unyielding distinction between gold and data. So, and that distinction is that gold holds on to its value if you don't move it. But if you don't move data, it's just garbage costing you money. So for me, as a person who working in a business consulting world, I work with several organizations, different companies, that when I interact with my clients, I realize that they serve and host huge amount of data that they don't do anything with it. Like every person just keeps a part of data on his or her laptop. That they, like, people don't know what kind of data is stored with a different side of the organization. There is no integrated system. And that's even harder when we go after the executive level, the C-suite personnel at a company, and want to start a dialogue and talking about like how they can leverage the data that they store already in their system. And again, a huge chunk of it is textual data. And the part which it becomes interesting is not only that data is already there, but it's important that the size of the data, it's becoming larger and larger as we go forward. So things that used to be like doubling up, let's say a couple of years, now they are exponentially getting large as we move forward with the expansion of like large technologies. And as I mentioned, the low expenses in data storage, data processing, and all of the technology around data analytics. So when you read articles within this era, people talk about like different attributes of big data, for example, 5 V's: volume, velocity, variety, veracity, value. But and we have like articles like a 3 V's or 7 V's. But to me, none of these really matters. I think at the end of the day, the part that we should care about the most is value. And I guess that's the key distinction between a data scientist and a machine learning engineer. So we're here to drive value, and that value in some industries and businesses means money. In some industries means security. In some industries means like humans' lives. But as long as we're not focused on the value we deliver, it's not really important like how you want to handle data. So later on, you'll see that there are folks, some practitioners that are mainly focused on writing the coolest, the most efficient Python script or R script or C++, whatever, or they optimize some machine learning algorithms or deep learning algorithms. And they're mainly focused on like making one model to be more accurate by half a percentage or whatever. So that's all well and good. But the main distinction, as I said, for a data scientist compared to those guys is you should deliver value. So there was this movie in 90s. It was called Jerry Maguire with Tom Cruise and Cuba Gooding Jr. And they had a very cool and edgy phrase, "Show me the money." And that's a term that I hear every day when I have meetings with executives. They don't really care like how you solve the problem, but they care about like what you found, what you solved. Like, is there a sort of cost that you were able to cut through analytics? Was there opportunities that you could identify through analytics? So that's the part that we should focus on. And today, with the agenda that we put together to talk about NLP, we want to address exactly that. So we want to show you like where NLP can come to play to drive value. So there are different definitions of data science, and I'm not going to spend too much on this, but just remember one thing, that a data scientist is not a statistician or a programmer per se. There is another part which is way more than being the person who's good with math or coding, and that part is storytelling and being able to bring context around your findings. And that's the part which is significantly important these days, because folks that are the actual decision makers in the marketplace usually, I'm saying like usually, like are those with backgrounds in a business or in accounting, or they had a degree in engineering like decades ago. So they don't necessarily understand the mechanics, the nuts and bolts of the techniques we use here. But what they care about is like what value we bring to the table. And that's the part that storytelling comes to play. And there is no university out there that tells you what would be the best storytelling strategy. It comes with experience and also getting involved. So I get these questions all the time from my former students and some of my junior folks that they work with me on a daily basis. Like, is it like useful to get involved in Kaggle competitions or some of the online courses out there? My answer is always yes. These things are good. These are useful. It helps you hone your skills in analytics. But those courses, they don't make you a data scientist unless you get your hands dirty by doing an actual work, by understanding like how you can define a value within the problem that you're trying to solve. All right. So let's have our thinkings quite aligned. So the process of modern data analytics solutioning actually starts off by identifying some of the key data sources out there. So if you look at this diagram from left to right, there are several sources of data, whether they are resident inside the organization or you identified outside of the organization. For example, what is resident in social media and Facebook and Twitter and Instagram and Pinterest of the world, and also some of the local databases that the company hosts. So the first step is to make sure that all those data sets are channeled into one place. They're integrated. That are in a way that they are, let's say, intellectually cohesive. They are basically talking to each other in a meaningful way. They can tie up in a straightforward way. And then it's all about like finding insights through data visualization, after performing data processing, some of the modeling where it can be ranging from like traditional statistical analysis all the way to traditional machine learning, and then going to even cooler areas like deep learning techniques and building a product or a process. And it's really important to understand that. So the last step of an analytics project shouldn't be just a confusion table or an ROC curve and just reporting out the accuracy of your model. It's good, but that's not the end of the story. The end of the story should be something in the form of a data product or a modification into an existing process or proposing a new process. And that's what makes you a real data scientist. And throughout this journey, usually you'll see that things break, things are not perfect. So it's all you should go back and check everything. Maybe it's the quality of your data, which is not great, contributing to the poor performance of your product or the processes. Maybe the way you integrated the data or data engineering piece and building the pipeline is not quite efficient. So again, you need to go back and revise that process. Or the modeling piece, it needs to transition from one model to another. So it's important to have that vision. So one other personal information to share: on a weekly basis, I interview folks to get employed for my own company. And when I look at the resumes, most of the resumes tell the same thing. So we always see like R or Python, and they all have taken a couple of courses on Coursera and Udacity. And it's not really distinctive when you look at those resumes. Like people have like really good GPAs coming from good schools. So the part that me and my colleagues care about is that vision, is that understanding of this slide per se, that it's not about just building out models for the sake of building out models. It's about delivering value. And once we transition to the core topics of NLP, I would like to have that vision as well, that we are like getting really deep into the textual data for the sake of building a product or a process. And we're going to share really, really interesting and different types of examples across different industries to show you exactly how this process works. All right, so going back to the process that I just mentioned to you, let's take a look at a traditional data mining approach, which is still quite relevant to building out analytics solutioning. So things across from identifying databases, and then you integrate them into a data warehouse, identify some of the core relevant subset of data for your process. You build a model, like here we call it data mining, where you can call it machine learning, whatever it is that is the key algorithm or a computer program, whatever you want to call it, which uncovers useful insights from the data, and you use it to feed into a pattern evaluation, and also basically a data visualization to derive the knowledge. So that journey, journey from moving from a raw data all the way to the useful knowledge where you can use for making active and also intelligent decision making is key. So with that understanding, let's move to the textual data. All right. So first of all, I think we all can agree on this, that textual data, they're everywhere. So if you are a person who is interested to start up your own startup company, you can think about like that would be one of the easiest type of data to go after, because textual data is everywhere. You can just write a very, very simple a robot to parse the data on web, and then you have the raw material to form your analytics pipeline. Or if you're the person who's already for an organization, for a company, then you can leverage the data, as I said, that is already resident in the data. So I can give you another interesting personal experience with you. I used to work for this client that they had a very large call center, and for every call that they received, it cost them $30 per call. So when they actually had the person answering that call. So when they replaced that traditional call center operation and they handled a portion of that calls using redirecting those calls to their social media feed on their Facebook and Twitter, and then applying some of the NLP techniques, now they are saving almost $15 million per year, considering the volume of calls they received. So just think about that. It's not anything magical per se, but it's important to understand that how a simple understanding of the value that is resident in the data and also in the NLP techniques can help you accelerate and also escalate the way you handle your operations. So with that, when we look at some common tasks in NLP, okay, so here the listed out some of the older and more fundamental aspects of NLP, like text classification, which still is quite relevant. And for example, sentimental analysis. Like the example that later on today we're going to see is a classic example of text classification. For example, you receive an email, it can be spam or it can be a ham, like a good email or bad email. So how can we determine like if the text is or an email is a valid email or not? So think about that example, and then you can generalize it to a ton of different examples. For example, one interesting one could be like the comments or some of the writings that you see on Amazon per order. There are some startups that are working as contractors for Amazon to distinguish which customer comments are legit and which ones are fake. For example, there are some comments that maybe a competitor company has hired some folks to write like negative comments for a product. So how is it possible to look at that text and understand that, hey, that's not a real negative comment? So those things actually matter to redirect like the future purchasing behaviors and also the key decision makings for the product owner today. Same goes for Yelp, same goes for some reviews for different movies, and even in when it comes to let's say a manufacturing industry, when we look at technician notes when they fix a product, it's really important like what exactly was the issue with that product. So it's really, really important how companies look at their textual data to identify fraud, waste, and abuse in their systems. So another part of the application of NLP where we all interact on daily basis is, let's say, the predictive word modeling, like predicting like what the next could be in a sentence. Like these technologies have already been applied in, for example, in smartphones. Like when you type your text, it can guess like what could your next word be. Or for example, when there's a typo, like what is the underlying technology that it guesses like what would the correct dictation for that be. All right, and also there are some more advanced, more sophisticated approaches to apply these techniques. For example, when we look at word embeddings and some language modeling, which later on Ali Reza will talk about, those in detail will come to play, and also sequence to sequence modeling. For example, you have a sentence and you want to translate it from language to another language. So how can we handle these type of problems in a meaningful way? So, okay, so let me take a pause here, and I want you to think about all these topics and see that some of these are all well and good. These are cool. Like right now, when you write your email in a Gmail, uh, you can just activate the functionality where it completes a sentence for you. So you can just like click on tab and it completes a sentence for you. And just think about it, like how does it really work? How can it guess the rest of the word? For example, you want to finish your email and it says, you type out, I look forward, then it completes it, I look forward to hearing back from you. So it used to be only predicting one word, but how is it actually possible to predict like multiple words in a meaningful way? So these are the things that when you look at sequence to sequence modeling, and also now one of the coolest and most interesting and trending areas in natural language processing is the chatbots. Like most companies like here in US, it started off by some of the large financial institutions like banks like Bank of America and Chase. They realized that they really can't afford to have like call centers here in US or overseas to handle calls. So they started off embedding some intelligent chatbots into their websites that actually has a very realistic look and feel of conversing with a human being. So that saves the company a ton of money and also provides a good experience for the customer. So that conversational chatbot is also very interesting, both from theoretical aspects and also in application. Now, one thing that I would love to underscore at this point is here, guys, NLP is a very sophisticated topic. And please just remember this sentence. If you want to remember just one thing from this workshop, NLP is a very hard task. So it's very, very difficult to really understand what is resident, what is the real information resident in the textual data. Like people can say some things which it's very difficult to understand whether it's a sarcasm, is it real, is it not real, is it relevant, is it not relevant. So it is a difficult task. And right now, I know several people that, at least in my network of friends that are doing their PhDs in NLP work. So all of these items, all of these bullets that you see here, uh, they are really, really huge. And at this workshop, we only have so much time to talk about an introductory high-level approach to all of these, but I highly suggest all of you, if you're interested, to get deeper at these topics, and you will find a ton of very useful and up-to-date material online. Just to give an example, for represent the meaning of a word, I mean, I'm talking about the third high-level bullet here, like for example, on word embedding. If you look at Stanford University's linguistic department, they have spent like millions and millions of dollars just building out technologies around that. So they have their own technologies, they have their own Python package like Stanford NLP toolkit. So I highly encourage you to spend some time to get deeper in those. And to understand where we basically position these types of packages here. So today we're going to use Python as our core programming language. So here you see that we have the Python core at the bottom of this slide. Then there are multiple Python packages that are built around that core Python analytics engine. And there are some other Python packages that are built on top of the lower level ones. For example, a part of pandas is actually fed by NumPy. So, and things actually move beyond that. So a package that today we're gonna use, for example, you see that it's scikit-learn here on the left side of my screen. So you can see that it's a higher level type of package. And also another package that I'm going to talk about is NLTK, which is not resident in this slide, but also that's one of the lower most lower packages very close to the core Python. And I remember back in 2004, 2005, there were some institutions out there that they used to teach Python only by focusing on NLTK. So, okay, later on, I would love to just show you one more slide, and then we're going to get our hands dirty with a little bit of hands-on work on the actual scripting in NLP. So, as I said, we're going to focus on some of the Python packages, which are really used for handling textual data. Like I'm going to talk about NLTK, but for example, I've done some projects using Spacey or Stanford Parser. These are amazing technologies. We don't have time to cover all of them, but I would love to leave you with a high level overview of these packages. Like for example, GenSim is a fantastic library that I highly suggest that you spend more time on it later on. But as I said, going back to NLTK, we're going to talk about some of the fundamental aspects of NLP inside the package. And we thought that it's most useful if we talk about these topics by also doing some real actual examples that are very relevant to the marketplace these days. So I would love to take a pause here. First of all, as I said, if you have any questions from everything that I just... Yep, we can take it from there. All right, so let me take a look at the list of participants. Please, if you are ready to continue, can you please raise hand in Zoom so that we know how many folks are ready to continue? All right, I see 1, 2. So when you raise your hand, I assume that you have the Python and also the data ready. Okay. Let's give it a couple of more minutes for the rest of the folks to get ready as well.
Also, let us know if you have any issues with downloading the data set.
Yep. Yep, seems like the majority of the folks are still working on it, so get more time.
If you have any problem downloading the data or anything in the link, just ask them and they can help you as well.
Yep. And a quick question, are you guys still able to see my screen? Right now I'm sharing a Jupyter Notebook.
Yeah.
Okay, excellent.
I've also shared the dataset file in the chat, so you should be able to just download it through Zoom if that's more convenient.
All right. So one more time, team, if you could raise your hand if you have both Python and data ready, that would be helpful. So I see only 2 hands in participants list.
There are also some who have pressed the tick button. So I think I have seen 3 like that.
Okay.
Maybe they have some trouble with those.
So yeah, if you have any problems, please let us know. Unless we can go ahead and get into the notebook. All right, fantastic. I see more and more folks are getting ready.
Also, feel free to use the Google Colab notebook if you don't have access to Jupyter Notebook right now. I just posted the link to Google Colab.
All right. I guess more and more folks are getting ready. Perhaps we can go ahead and jump in. I can start off by just talking about the approach, the type of the problem that we're trying to solve here. And as you're getting ready, I try to slow down the material that I present so that more and more folks join for the more meat of the work, if you will. All right, so and Parvati, let me check with you as well. Do you agree? Let's jump in.
Yeah, you can start. Yes.
All right, excellent, excellent. All right, so guys, couple of things. So first of all, we're going to import the data that Ali Reza shared with you. And the data, which you'll see in a minute, contains a set of comments or emails, textual data, and also some labels as spam or ham, meaning that if it was spam or it was a legit good comment. And the goal here is to build a classifier that can distinguish between good ones, the ones that are labeled as ham, and the ones that are labeled as spam. So there is a process moving from raw data all the way to building out models and training a classifier. And so I'm gonna start off by first reading the data, and then we need to pre-process the data. So here, the first thing that I'm going to focus on is remove the stop words. So we'll see that there are some words resident in a text that they don't carry like really useful information. Like they are working as a noise in most applications. Like we're gonna see some examples. Another thing that we're gonna do here is, sorry. Another thing that we're gonna do here is tokenizing a sentence. And we're gonna see an example, like when you have a sentence, how you can actually break it down to have like word by word. And there are several algorithms to handle tokenizations. For example, if you have the word don't, D-O-N apostrophe T, should we count it as one word or should we break it to do not and have two words out of that? So if you think about that example, there are many exceptions in English literature to handle having apostrophes, having hyphens. So it's important how we want to handle that tokenization. And also, another part of pre-processed data is stemming and limitization. Where in some contexts, when you look at the word go, it's really important to actually get to the root of the word. When we have go, goes, going, went, is going, we really don't care about those combinations. We want to reach the core or the root of the word. And technologies like stemming or limitization actually help us to do exactly that. So when we compare two texts, we want to make them as comparable as possible or as distinctive as possible. So first of all, I have a sentence. I want to get rid of some of the words which are not really useful. We're gonna break down the sentence and also apply some algorithms like stemming and limitization to get to the root of the word. All right, so I'm gonna cover this part first, and then I'll pass it over to Ali Reza to talk about another aspect, another key aspect of the analytics work. Like I would say feature engineering of the raw data. So remember, for training a supervised machine learning model, you want to have some features, right? And in textual data, there is no feature. You have a sentence or a paragraph or whatever, or maybe you have a book. So it's just a bunch of words, or if you think about it, like sequence of characters sitting next to each other and forming a text, whether again, whether it's a sentence or a paragraph or a page, whatever it is. So it's important that after handling this pre-process, we build some features. So we'll learn about some of the old or traditional approaches to building out these features like TF-IDF, term frequency, inverse document frequency, stuff like that. And even some even older approaches, which still are quite relevant. For example, the length of the text, or the number of times that you see punctuation in the text, or the percentage of punctuations divided by the length of the text. So we'll see that how you can engineer some features of the raw data. And then we're going to use those features, to train a machine learning model. And then we will evaluate the performance of the model. So these two will be covered in our in the first part of this workshop. First section of the workshop. All right, and then we can transition from this problem to more advanced and more ML/deep learning based technologies. But we believe that having this foundational understanding of NLP solutioning is significantly important and impactful when we talk about some cooler cutting edge modelings like recurrent neural network, LSTMs, and also when you want to build chatbots or sequence to sequence modeling. So all of those techniques in a way are built on top of these foundational and traditional approaches. So again, before I jump to the data import, can you please just raise hand again? I want to see like how many folks are able to code along with me. I only see 2 hands. All right, 3. Come on, folks, we can do better than that. Awesome, awesome. Yep. It's like a vote count in Nevada. So we have to give it some time. All right. Yeah, I guess we're moving slowly but surely. All right. All right. So, okay. So the first thing that I would like to do is import NLTK. So what is NLTK? Natural Language Toolkit. As I said, one of the most powerful and one of the most sophisticated, I would say, NLP packages out there in the world. It's not only working for Python, but it's what's created for Python. So if you want to see how large it is, just dir it. So if you dir anything in Python, it shows you all of the modules or features that are created by the community for this package. And I'm just quickly scroll down and I'll see how large it is. So any of these are modules or attributes assigned to NLTK. So it's a huge package. It is unbelievably well developed. As I said, it's very old, and for different needs that people found in NLP, they added something to it. So again, I suggest that you spend some time. There are books written only for NLTK. So if you search on Amazon, you'll find a couple of options. So the first thing that I would like to do is first, make sure that my machine has access to the list of stop words that are defined for NLTK. So if you're coding along with me, make sure that you do this. NLTK.download stop words. All right. So see, because I have already downloaded this, it tells me that, hey, that's true because I already have access to it. But please do this for your machine and make sure that you have access to it. And the next thing that I would like to do is from NLTK.corpus import stop words. And after that, I would love to see stop words dot words, and I want to specify the words. I want to specify the language. It's English. Show me all these stop words. So see, it's a very long list of words that, according to the community in NLP, they don't carry that much value. So when you have a sentence and you want to specify whether it's spam or ham, having the words our or we or myself or was or were, I mean, they can be helpful, but not that helpful. So they call them stop words. And usually we would love to eliminate these words when we actually want to pre-process the data. So going back to our way of thinking, when I have some data and I want to pre-process it before building out any ML models on top of that data, one of the first things that people do is identifying stop words and removing them from the sentence. So, all right. Okay. So, all right. Now we know that, first of all, how we can download these softwares, which is getting updated by the community, and also um, how it is shaped up. All right. Now going back to our data. So this is the part that I import the data that Alireza shared it with you, and it's already stored in the same directory for me where I have my notebook opened up. So I created a module. I just call it raw data, and I open the name of this file dot tsv is SMS spam collection, and I read it. All right. So when I have that data in my memory, just show me 0 to 500. So one thing that it sucks, I know that it is T delimited. So one thing that I can do is here, I say for raw data, replace tab and also any enter with enter, and also then split it with respect to that enter. All right, now it is cleaner. See, I see that the label is ham, then I see this sentence, then this one is spam, and this is the sentence. No, okay. So I would love to store this in a new object, and I call it parsed data. All right, so if I want to just take a look at the first 5 entry, the first 5 entries of this, it's much cleaner than what we had before. All right. Now, see, okay, the way that the data is structured in this text file is very, very raw. So see, the first element in this list is the label for the second element, right? But what I eventually want is to actually separate them out. So, all right, I use some of the basic Python list technologies to separate out the labels from the actual text. So I will do this. Label list is the parse data, and I know that it starts off from the first element, but I need to skip by 2, and then the actual test list is parse data, but I have to start from 1. So when you run this, let me do it right here within this cell. Print out the label list, the first 0 to 5 elements for me. See, now they are only labels. And do exactly the same for the second object. What did I name it? Tests. All right. So see here, it just includes the actual narrative, the actual test. Okay. So I want to do a really quick check. So usually in these things, we have to make sure, because we didn't see how this data ends, and sometimes the list is ending with, for example, not a real label. So for example, you expect it to be a label, but it's not really a label. So it always helps just to check out the length of both labels and print the length of this guy, and also the length of this guy. Ideally, we would like to see that they both are equal, but let's check it really quick. Oh, see, this is an example that I was talking about. The length is not equal. So later on, it can create a headache for us. And I would love to see that what are the, what's happening in the labels. So show me in the label list, show me the last 5 elements. Oh, see, there is an empty space. So we need to be careful about this one. So, okay. And there is a reason that I would love to, I love for you guys to see that how these things can happen in real life projects where you have to spend time to clean it up. Alrighty, so I know how to handle this. So let's make it a little more clear and more user-friendly, if you will. So import pandas as PD, and let's do that. And then I would love to convert this messy situation into a clean pandas data frame. So I would say PD that data frame. Now I would love to create 2 columns. The first one, I would love to call it a label. And the label is actually the label list. But now that I know the last one is actually an empty space, I would say use everything except the last one, up to the last one. All right, and now I want to create my second column, which is call it the body list. Yep, and this one is my test list. All right, so let me run it. It's much cleaner than what I had before, but it's a little my style, but let's save it up in an object. Let's just call it full corpus. And now just show me the head. All right. Look at this one. I have a date on Sunday with, well, that's a ham. Okay.
Excuse me, sir.
Yep, go ahead.
Sir, why didn't we use the direct function of pandas read CSV and
Yep,
use
yep,
separator as tab?
Absolutely, absolutely. You could do that. And later on, I'll show you. Yes, there are. Okay, so the goal here, and that was a wonderful question. Thanks for asking that. For when I go back to this purpose, when I talk about like reading the data, we would love to start from the most fundamental ways, but you're right. You can start from pandas, and even you can go beyond that when we talk about some packages like Keras. So even you can bypass even pandas and go directly to the data and push it to memory. So we started off by the most fundamental and basic approach. But you're absolutely right. You could directly read the data through pandas and using tab. But my goal is just to show you these little tricks to have those in under your belt in facing like future problems. But I hope I answered your question.
Yeah,
But
understood, sir. Thank you.
as I said, yes, but by no means I'm suggesting that this is the only way, but the goal here is to show you the most fundamental and basic approach. But later on, this is not the approach that I'm suggesting to apply in future applications, but this is an introductory level approach towards this problem. All right. Um, Okay, actually, that was a great suggestion. Let me uh, rewrite all this approach based off what this gentleman just suggested. So I could say full corpus is equal to pd dot read csv. What was the name of that file? This little guy. Oops. And then I can specify the separator to be tab and specify the header to be none. Full corpus, show me the head. And then I can assign the labels that they'll want it. So I guess this is what you had in mind. Yep, I could do all of these in one line. But I wanted you to go through that pain to have that experience, like before using the tricks. Like one thing that they say in poker, before you start the cheatings, let's learn the rules of the game. So I didn't want to start, and later on you see that we don't want to start with these little tricks. I know that it's easier, more convenient to take advantage of pandas, but later on you see in real life projects, starting off by pandas, it can create a ton of headache for you because of the nuances that are resident in the data. So it's important to have this deeper knowledge in your back pocket. So where it's needed, you start with a deeper level and not just jump into pandas or some other packages like Spacey or whatever. All right. Any other questions, guys?
Hi. I don't have a question, but I didn't get a chance to fully look at the code you put for using the NLTK library or package. So I would like to go through that code again. So if you can share with us in a chat or however it is.
Yeah, I mean the code that as I'm writing right now, or
yes, just the main script. I just wanted to see, like, I didn't get a full chance, but I was listening to you and also trying to write the code. I didn't fully understand that. So these steps.
Absolutely. So perhaps since we haven't done any sophisticated so far, do you think it's helpful if I just give you the latest cell, or do you want to get access to everything that I just typed?
Yeah, before that, using the NLTK.
All right. So let me think. Like, what would be the most efficient way? Okay. So Let me ask Ali Reza. Ali Reza, is there a way that, because as I'm typing out into this notebook, is it possible that I attach it to the chat so that team have access to the latest version of the notebook as I'm typing out? Like I can attach it as I am adding more content to it. Is it a?
Hello, sir. I think it's
try
possible
adding
to
it to the.
I'm sorry. Go ahead.
Oh, you can go ahead. Go ahead.
I think it's possible using Google Colab, since you can add, you can create a link and share it with the participants if it's through Google Colab.
But is this code not available in the GitHub folder like you shared, like the?
I mean, I'm sorry. What is available in the GitHub? You mean the completed text script?
Yeah, the completed script is available, like, because I can see a notebook there.
So
yes.
That's gonna be me.
No, I'm trying to think. So because no, yeah, on GitHub, we're going to add the completed version after the session, but I'm thinking perhaps, for example, right now we have reached a good milestone. Maybe we can just add this to Google, I mean, to the GitHub right now. And as I transition to the next topic, I just type out a couple of more cells and add more content to it. Does that work?
Yeah.
Okay. So, all right, let me do that. So I can push this out to GitHub really quick. So please give me 1 minute, team. All right, so Alireza, once it's done, what it is on GitHub, please let us know.
Sure, yeah.
Thank you. All right, so as we're doing that, let me just speak to the next approach that I want to show you. So the technique that we want to present to you is tokenization, like when you have a sentence and you want to break it down per elements into the sentence. And again, I want to start from the lowest level of approaches in this area. And I want to use the regex, regular expressions, to do that. So going back to the previous gentleman's question, like why didn't I use NLTK tokenizers, or why didn't I use scikit-learn's tokenizers? Yes, there are several more sophisticated and quite frankly, even easier ways to approach this. But again, it's important to have that deeper understanding around these approaches. So for example, NLTK was written on top of regex. So wanted to share the lower level approaches in this era. And after you can handle this one, then you see, just like the example that I shared with you here, if you can understand the approaches that we went through within these lines, like transitioning to a more capsulated approach to handle that, that can be much easier and straightforward. And when things break at this high level approaches, then you know where to look for in a lower level aspects. So, okay, so I'm gonna start talking about the tokenization. And so for this one, I'm gonna take advantage of a Python package. Actually, I shouldn't call it a Python package. It's own actually. It's regular expressions. When initially it was written for HTML, but it was embedded into almost all of the trending programming languages in Python or R or C++, whatever. So regular expression. So I would say, let's not spend too much time in describing it, but show you more examples. So first of all, I will import regular expression. And a quick question, Alireza, is the notebook already on Git?
Yeah, I just pushed it and shared the link with the theme that they can download it from here.
Yep. So it doesn't include the new parts here in cell 21 and cell 22. After I complete this part, like added a couple of more cells, we'll update it. All right. So just to introduce how Regis works, I'm gonna add a bunch of examples here. So the first one, I would love to call it regex test. What should I write here? This is a made up string to test two different regex methods. All right, this is my first string. Then I say I need another one, test, and I just call it messy. And let me just copy paste this. Actually, yep, copy paste the same one, and just add a bunch of empty spaces in the middle. And let me just copy the entire thing and paste it here. And I just call it regex test messy 1. And now here I add a hyphen. And again, even here, I had another one here. And then I just put a backslash. And here, maybe an asterisk and a bunch of these guys. And then another hyphen, and then or maybe just a little more asterisk. So, and just tilde here. All right, super messy. And okay, just make it a little more fun and hyphen. Okay. All right. So I have 3 examples, one sort of normal, and then another one with a bunch of empty spaces, and one super messy version of these things. And now I will apply some of the regex functionalities in this one. So first of all, I would love to do this, regex split. Okay, so the basic format is you have to specify what you want to do with the text and then specify the text. First of all, I would say I want to use one single white space as the key thing that I want to do with the data. And then this is the first data set that I want to apply to. So when I run it, what it does is it actually breaks the data with one single white spaces. Okay. So that can be one example of tokenization. When things are nice, when we are living in a dreamy world, when there is no abnormal situations in a textual data, this thing can play out well for tokenizing a text. Not a perfect approach, but it can work well. But let's try it out on the second example, the messy one. So if I do that, see, the output is not perfect because it identifies single spaces. So this is not exactly what I wanted. It gives me a lot of garbage. So maybe I just comment it out and I just say, not the best approach. Okay, but let's do a single trick here. So if I just copy this and say, hey, forget about a single space, do a single and even more. So now it is clean. So this little plus, so these are, now we are speaking with the language of regex by just adding one plus. We handle the situations like when we have like multiple spaces. But now we know that what exactly it's doing is searching for white space. But before I do anything with the third one, I think we all agree that neither of these techniques can work here because there is no space. So what we should do is, first of all, get rid of these special characters first, and then search for any non-word characters. So to handle that, I say regex.split \. Now I use a capital W for word. I'm sorry, when it is capital, it's non-word and plus. And now I search for text messy one. And now let me run it and see it's working like a charm. It removed all these special characters, identified the actual words, and tokenized it beautifully. All right, so what exactly are we doing here? We are searching for space and we're breaking a sentence. Another way of handling this is using another regex functionality, which is, oops, edit, undo, +++. Okay. So another thing that I want to show you is another regex module, which is refind all. So / with the same format, just show me one or more non-empty spaces. And let's start with the first one, retest. Again, it's working. So we had seen this before, right? So let me just copy this to save some time, paste it here, and run the same thing on messy. Again, it's working. So now it's looking for one or more spaces. Now, again, copy. Oops, so it's not working here. So how can we handle this one? Again, in this approach is the reverse of what I did before. So before we were searching for spaces. Now I would love to search for like for characters. So see, if I just change this module with find all with small w, now it is working like a charm. So as I said, maybe I just show you one more example with regex, and then we can move to the next topic here. And before I show you this example, have you had this experience that you go to any website and they ask you to enter your email and password, and you just put some random characters and it tells you that, hey, that's not a legit email, put a legit email. I think we all have experienced that. Or you want to create an account and they tell you that, hey, this password, it should have a capital letter, small letter, some special characters, and the length should be at least whatever, like 8 or 12 characters. And you just put out some random things and it says, hey, it didn't comply with the requirements we wanted for the password. What it's actually doing behind the scene is applying regex. So in my normal classes, one of the homeworks that I used to give my students is actually building that capability to test that, to make sure that the characters or all the requirements are met when building out like checks for both emails and passwords. So let me show you these couple of examples. And again, this is introductory. It's there is, I think, one separate course only on regex. I think I saw it on Udacity or Coursera. So it's a huge topic. So let me create three random modules. So PEP 8 PES, and I just call it. And team, do we know what is the difference between single quotations, double quotations, and triple quotations? Let me take a look at the participants. Is it super clear to everyone? Can you just raise hand? Or if it's not clear to you, can you just mention in the chat? Or we can just spend a minute to talk about like what's the difference between single quotation, double quotation, and also triple quotations. Anybody has any question on those?
I think I know what they mean, sir. Single quotation, I think it's only for a word, to put a word in it. Double quotation is to put a sentence, and triple quotation is to put multiple sentences together.
You're right, but it's partially right. So you're right. I mean, it can be word, sentence, but multiple sentences. But that wasn't the actual initial intent when the Python creators like Guido or some other folks built out these three things. And let me show you why. So in single quotation, and first of all, let me start from the beginning. So you can say, my book is expensive. Okay. So you can use a single quotation and Python understand that it is a text, right? But if I say Ali's book is expensive, all right, see, in English, we use apostrophe to say like the book belongs to Ali, right? But now Python thinks that the text starts here to here and everything else is becoming super confusing for Python. So although we have a single quotation left here, it does nothing. So if I run this line, let me actually run it. It gives you a syntax error. It really doesn't understand like what's happening. So because of situations like this, you put everything in double quotation. Remember, when it was my book is expensive, it was okay. Although it was a sentence, it was okay. But to avoid situations like this, they also created double quotation. Okay? Now, why do we have triple quotation? Let me show you an example. Let's see, copy and paste it here. Ella's book titled as Victory is expensive. So see what's happening here. Python thinks that the sentence started here and ended here, and another one started here and ended here. Now the word victory is standing alone. So if I run here, again, invalid syntax. So to handle this, instead of double quotation, you have, oops, F11. You have triple quotation. Now everything is clear. So does it make sense? Like why we have these things? And another reason for triple quotation is that you can have everything in multiple lines and still it works. It doesn't work with single or double. So are we clear on that? Like why we have single, double, and triple quotations? I hope this example helped. So just to quickly recap, it's not really about like having a word, sentence, or paragraph distinctions, but to avoid situations like this, or having like double quotations in the middle in a sentence, we use triple quotations. All right, so since we're going to push this on Git real quick. Yep.
Participant. So they asked, why is the data in real use cases when it is text so messy?
I'm sorry, can you say that again? I had a hard time hearing you.
Yeah, they ask, why is the data in real use cases of NLP very messy?
Okay, why is the data in real life use cases very messy? Okay, two reasons. One is because we as humans, we really don't care. Not everybody pays attention to what they type out. And another reason is some of the key data entry portals are not designed efficiently. To give you an example, in some manufacturing applications, it's really important where a technician, when he or she wants to type out their review of the fix that they applied on the unit, they need to be able to distinguish what was the issue, what they did, like, I'm sorry, before that, what the customer's complaint was, what the issue found, and what correction they applied. So complaint, cause, and correction. They should have like 3 different areas to put their entries. But in many real life situations, you see that there is no distinction between these 3 categories. So the technician has only one place to type out, and things can become super messy for the person that later on wants to analyze that textual data. So if I want to see that if the right fix was applied to the issue, then I need to do some of the work that I'm doing right now to be able to distinguish like which part of that paragraph is actually relevant to complaint, which part is relevant to the issue that was diagnosed, and which part is about excuse me, and also which part is about cause, complaint, and correction. and which part is about the complaint that the customer had. To give you a real life example, I take my car to the dealership and I say, I think that this part, like the compressor in the engine, is broken. That is my complaint. But after diagnosis, they realize the issue, it's not really the compressor, it's a different part. And the correction is that they replace that part. So these three things are different. And using NLP, after all, I need to be able to distinguish these three. So to answer your question, first, human, they are not that careful when type out the numbers, especially when it comes to social media. When you look at like posts on Twitter, on Instagram, on Facebook, on Yelp, people just type random stuff. And they use, for example, like when we do texting with each other, when you do this, actually, let me put it in the text. I'm doing great. I'm sure that we all do things like this. So how the heck the algorithm needs to understand that this is not a typo. This is actually us trying to be cool. So it starts us, or I'm doing great. So now you know that I'm just being sarcastic. It's not real. So the whole semantic of the sentence, the whole message that I'm trying to convey to the other side of this communication is totally reversed. I'm not doing great. I'm super bored, right? Or now the things that are super trending in NLP is emoji analysis. So this, I'm doing great. But now this little emoji, this can actually mean that, hey, maybe I'm doing great. Things are boring, but it's still good. So this is a part, if you remember the sentence that I asked you to remember and use it as a takeaway from this workshop, NLP is hard. It's a difficult task because of all these nuances us as human beings bring as complexity to the marketplace. All right. So because of the time restriction, and I hope I answered your questions. So I don't want to spend too much time on this one. So now we know how to remove, excuse me, how we detect stop words from a sentence, and also how we tokenize a sentence. Now, just let me quickly show you two quick examples of stemming and limitization, and we're going to revisit this after we saw some feature engineering topics. So transitioning, oh, by the way, let me save this really quick and push this to Git. Just 1 second. Yep. Yeah, while the updated version is getting pushed on Git, I recently spoke with this new startup that what they're trying to do is not only looking at the textual data, but also identify the tone from the sentence. And then, for example, when they receive a complaint on social media or whatever, and they want to redirect it to an actual human being, they want to escalate the issue, they want actually try to link it to this person with the similar personality level. So if I'm the guy handling complaints and I'm a happy person, or I'm an agitated person, I'm a nervous person, they try to redirect the accurate or relevant type of complaints to me. and not everything randomly gets assigned to people. So this is the next generation of, let's say, complaint escalation using NLP. So not only just reading the test, but also assign a degree or personality type, sort of. And things like emojis or sarcasm or jokes or things that are specific to different languages can become very sophisticated. And especially when it comes to, like in the US, you'll see that in complaints we have sentences that partly English and there are partly Spanish. So it started with some words in English and there is slang from Spanish just thrown somewhere in the sentence. So again, it's difficult, but we're trying. So the community is building up some knowledge around it. So let's be patient. So going back to that stemming. All right, so I'm going to start with, by the way, both stemming and limitization, there's a huge literature around them. And I'm just going to show you some, first of all, let me just type out some famous stemmers. For example, one is Porter stemmer. One is Snowball. Another one is Lancaster stemmer, and there are also some regex based stemmer if you want to Google. So for today, what I'm gonna do is I'm going to generate one from NLTK, one Porter stemmer. So I create a module. So as I said, I would love to reach the root of the word using stemming. So to show you an example, print what? Print ps.stem, and let's just use the word grows. Okay, and let me just copy this and paste it 2 more times. And now I use growing and also just the word grow. When I run this, see, it understands the root of all these 3 is the word grow. Okay. Now it's good, but remember, it's not perfect. Let me do this example for another. So let's do running, and maybe runner. When I execute this one, it understands the root of the word running is run, but it assumes that the word runner, it's its own word. So again, just have that in mind, that these algorithms are good, but they're not perfect. We need to be very careful about this. And another, let me quickly transition to another topic that I would like to talk about on the notion of limitization. So let's do this. Let me create an object, call it WN for NLTK dot word net limitizer, which is super popular. And also we had already, let me do this again really quick, ps NLTK dot port stemmer. I just created 2 objects for limitization and stemming. So just to show you the distinction between these 2, when I say ps dot, actually let me start with print ps dot stem, the word meanness and also the word meaning, and I run it, it says the root of the both is mean. But when you think about it, is it really? Like here, we're talking about the person being mean, but here we're talking about things like actually mean something. So because of these instances, we need a whole new approach, a new algorithm for going after situations like this. So I go back to my WordNet and let me do this. Copy this for the interest of time, and I just replace PS with WN. And remember, WN is the module I just produced here for word limitization. And I run it. Okay, it says there is no word stem, and he's right. Me being lazy created some problems. So for WordNet, we actually need to use the module limitize, not stem. Okay. Oh, small l. We don't have time for these silly errors. So yeah, it takes some time, but now it comes back and tells you that, hey, when you limitize the word meanness, it's actually meanness. We're not getting to the root of anything. And even the word meaning, we don't expect it to actually comes back to us and tells you that, all right, the root is mean, because we're not searching for root. It's just us checking if things are being semantically meaningful or not. Just to give you another example, which is pretty famous in the in the literature, now that we have these two set up. So if I search for the stem of the word goose and also geese, we know that geese is the plural form of goose. And when I search it for the root of these guys, see, all it did is just dropping the E at the end of the word. And we know that it is not right. But now I apply the same thing on limitization, and I change it with goose and geese. And when I run it, it tells you that they both are goose. So the combination, all I'm saying, the combination of stemming and limitization and using them in an intelligent way, they are foundational to clean up the text. Remember, everything that we just did is just for data preparation. And using stemming and limitization, and we'll see them later, maybe in almost an hour and a half from now, of how they are tied back together, like how we can build them up in an analytics pipeline so that we leverage they both to avoid entering any noise in the data. So let me take a pause here, and I'm going to stop the first part of my lecture at this point, and I'm going to pass it over to Alireza to talk about some of the feature engineering aspect. And why don't we just push the latest version on Git, and then
representation models are based on vector space models in algebra. And let me walk you through an example that would clarify what a vector space is. So suppose that out of the whole dictionary or vocabulary, I'm going to pick 3 specific terms. Let's say like term 1 is cat, term 2 is sport, and term 3 is politics. And now I'm going to try to use this 3-dimensional literal example to represent different text data. So assume that I have this document 1, and I want to use my 3D vector space to produce a representation for that document. One thing that I can do is that I can compute this identifier vector for document 1 using just units vectors that would point into the direction of the term that it has in it. So if the document 1 has term 1 and term 3, this identifier vector is going to like point to the direction of those two terms. And document 2 has different terms, doesn't have term 3, so the vector is going to point in a different direction. So this is the basic concept of how word representation is going to look like. All right, and like in the following sections, mainly in the basic approaches, we're just going to add on to the dimensions of this vector space. So let's see the first one. One-hot encoding is a pretty famous and widely used encoding technique in signal processing. And we're going to see how we can apply this to text data. So let's assume that we have this dictionary or vocabulary. And like here, I'm trying to also introduce some of the jargons that's being used in the NLP. For instance, vocabulary, it's one of them. So vocabulary basically defines as a set of words that you have in your dictionary that it structures your knowledge, your linguistic knowledge. So for each word in the dictionary, W1 to WV, there is a specific ID assigned to it. So for instance, the first word has an ID equal to 1, and the last word has an ID equal to V, which is also the size of the vocabulary. Now we have this sentence, sky is blue, and we want to perform one-hot encoding word representation on it. So what we're going to do is that we're going to sweep through the sentence, sky, blue, and then for each of them, we're going to build this V-dimensional row vector. So what is a one-hot vector really? One-hot means that like all the elements are 0 except for one of them, which is hot. And then in a binary fashion, the one-hot vector would point to the word that corresponds to this word in the dictionary. So if the sky is the ith word in this dictionary, then the ith element of the one-hot vector is going to be equal to 1. I mean, same thing with blue. So this way we can, stack up these row vectors together and build up a whole matrix that would represent this sentence in a one-hot encoded way. Okay, let's try this. And in the coding sections, you can just, tag along with me and try to code it up. I avoided like large corpuses of text so that you can just like code up with me. So let's try to code this up exactly as we describe this. I provided this toy vocabulary set that has yellow apple, dog, all the way to sky. And there's going to be like the IDs associated to each one of them. So let's define the function. The function is going to take in the text and output the one-hot representation of that text. All right, in order to do that, let's first initialize the one-hot representation with an empty list, right? And then what we're going to do here is that we're going to, for each word in the text that is splitted word by word. Now for each word, we're going to initialize this row vector. So we're going to need a vector, which is all zeros. And this 0 is repeated by the name of by the length of your vocabulary or your vocabulary size. Okay. Now we're going to check whether this word exists in our vocabulary or our word knowledge. So we're going to check if word in vocab.keys. So if this is true, then we're going to take a look at a row vector and set the corresponding element to 1. Now, what is the corresponding element? That's going to be the value of that word. So this is going to be vocab of that word. So this might not be like the most efficient way to code it up, but the logic just falls through every step. So let's run this. Warning, run anyway. Oh, I forgot to append. All right, so like obviously we need to also append this vector to our one hot representation. Let's see, what is the problem here? Oh, this is just an indentation problem on the 5th line, and also right here. So I just accidentally added an extra indentation. This should work. Nope. Let's go through the steps to see. I probably messed up an indentation somewhere. Okay, let's see, it's right here, and then here, 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 and also here. Okay, yeah, you got to be really careful with indentations. All right, so let's run this function on this little sentence that I have here. The sky is blue and the cat is black. Well, cat is not. Oh, okay, I forgot to run this. All right. So as you see for each word, if it exists in our vocabulary, we're going to flag that corresponding element to 1. And this is what a one-hot encoded representation looks like. This approach is not really practical, and you're not going to see a lot of examples in like real world where they use this approach. Like, what are the main drawbacks here? Where the first one is that as you look at this matrix, it's really high dimensional. Like if you have a really long sentence, this matrix can, explode in dimensions. And also, if you just take a look at it, this matrix is really sparse. And like most of the entries are actually 0 with just like very few elements equal to 1. And like basically in matrix calculation, we do not like a lot of sparse matrices because sparsity makes computation a little bit challenging. Like for instance, if there is somewhere in your code that you need to invert this matrix, you're going to run into a lot of computational problem because this matrix is basically like numerically this is 0. And one other drawback is that this representation doesn't really capture any semantic relationship between the words in the vocabulary. So it's like totally blind to the definition of the words. All right, so let's move on to a slightly more sophisticated classical approach, which is called bag of words. Well, bag of words, as its name, treats the text literally as a bag of words. So it ignores any like context and word order. So you just have this bag of words for your sentence. Again, we have a vocabulary, and our corpus has like n documents, and we want to represent each document with a feature vector that is built through the bag of words method. So for each word in the vocabulary, we're going to count the number of its appearance in our document, and that's going to be the corresponding value of the feature vector. So for instance, if Wij appeared, how many times in the text, you're going to just plug in the value here. All right, let's quickly try this. In this example, I'm going to use the scikit-learn count vectorizer, which is going to help us to count the different words and build this matrix. All right. So this is our toy corpus. you can look at each element of it in a way as a document. And this is like 1, 2, 3, 4 different documents. So first, I'm going to initiate the count vectorizer that would count the number of appearances. And then I will build the bag of word representation by taking this instance and then fitting it to my corpus. Right. So what this function is going to do is that it's going to, first of all, extract our vocabulary from this corpus. And we can get that by looking at this. So if we just print vocab, so after we fit the count vec model to our corpus, we can print out the vocabulary to see these are the vocabulary, and each word has the specific ID associated with it. Now, let's move forward and try to build bag of representation out of this corpus for each of the documents. So for each document in our little corpus here, we can basically say that I want to look at the bag of words of, let's say, the first document, which is going to be corpus 0, right? And that's going to be bag of representation 0, and for printing purposes, I'm just going to convert it to array. Right. Add the loop. Okay, so this is the bag of word representation of the first document. Obviously, it's showing the number of appearance of each element of the vocabulary in the first document, and we can actually see this work, like any of the documents. I'm just going to define this as a variable. So, for instance, for the fourth one, there is the feature vector through bag of word representation. But let's see the drawback of the bag of words.
Sorry to interrupt. We have a question.
Oh, sure.
We have a question in the chat, and
okay.
Bag of words is nothing but the count of words from the vocabulary, right?
Exactly. Yeah, but just stacking it in a row vector. That's exactly it. So to that point, let's see a drawback of this. So let's say I have a new document, dog and dog are friends. And we see that like rarely any word of this new document appeared in our previous corpus that we used to train the count vectorizer. So as we see, the bag of word representation of this new sentence that I added is like a highly spaced feature vector that may not convey a lot of information about this sentence specifically. So a few advantages of bag of words is that, as we saw, and as our friend mentioned here, it's just counting words. So it's pretty straightforward and easy to implement. And since it's building one vector for one document, we can actually convert these vectors. We can actually compare these vectors in the vector space and quantify similarity between different documents. So that's another advantage of it, that it captures semantic similarity between different documents in the corpus. But the drawbacks are that, again, it's blind to the meaning of the words themselves. And also, if we have a new word, if you have a sentence that's built on top of absolutely new words that we haven't seen in our vocabulary, this is gonna gracefully fade. And again, since it's a bag of words, it totally disregards the order. And as we know, like in language, order matters a lot. So we're gonna lose a lot of information there. Okay, so moving to the next classical approach, and actually I think the last classical approach that I'm gonna mention, we will be explaining TF-IDF that Ashton introduced in the first part. So TF-IDF basically asks this question that, are all the words equally important in a text? Like if you just pull up like New York Times website, you're gonna see a lot of like ads and things like that, words that are not really important. So TF-IDF is there to actually curb this limitation. And it stands for term frequency and versus document frequency. And the idea is that let's assign an importance coefficient to each of the words. And the way that we quantify this importance is that the importance is proportional to the number of times the specific word appears in a single document. So for instance, word W is important for document DI specifically if it frequently appeared in it. So let's assume that we have a set of articles, and like in one of them, there is a lot of election word. So as we might expect, election will be a good indicator of what that document is really conveying. So there is that, but TF-IDF doesn't stop here and actually kind of normalize this coefficient by saying that importance is also inversely proportional to the usage of the same word in all of the documents. So for instance, I pull up a document and there's a lot of ands in it. So my naive guess will be that and is a good indicator for the information of this document. But as we see, that we can find like these type of words in other documents frequently as well. So you need to inversely normalize your importance coefficient by the number of times this word appeared on all of the documents. So there are two variables in TF-IDF. First one, term frequency, TF. For a specific term in a specific document, the term frequency is measuring the proportion between the number of times term T appeared in document D divided by the total number of time like all terms that appeared in D. So basically the percentage, how much of the percentage of the document is specifically word T. And then IDF, inverse document frequency, for each term in your vocabulary, you're going to compute an inverse proportion, excuse me, an inverse proportion of the number of documents that has word T in them by the total number of documents. So you're basically saying how, like across all of the documents, how important is this word? And then at the end, you just calculate the TF-IDF score by multiplying these two parameters. Is there any question on this before we move on to actually try this on? Okay. So in order to implement TF-IDF, I'm going to use the TF-IDF vectorizer from the scikit-learn library. And let's see. So I already like loaded the model here under TF-IDF. And let's actually go back to our previous corpus. This one, I'm just going to copy and paste it just so that we have it here. So for this text, for this corpus, let's compute the TF-IDF scores. So what I'm going to do is that I'm going to define the bag of word representation, TF-IDF, which is going to be the model specifically fits to our corpus. Okay. All right. So if you fit the TF-IDF on our corpus, this is going to give us like two things. The first one, actually, let's try to visualize it with pandas. I think it's going to be more visually appealing. So I'm going to build a data frame. Two things. So the first one is the vocabulary. So we're going to see the vocabulary extracted by our model, specifically for this corpus. It's going to be get feature names. This way we can actually see what are the words in our vocabulary. And we can extract the IDF score by looking at IDF. Right, so and actually let's go ahead and print this data frame. Oh, I forgot to put a dot in here somewhere. Okay, so this is a dot. All right, so these are the vocabularies in this little corpus that we have here, and the corresponding TF-IDF scores that is calculated. Now, there are multiple variations of TF-IDF, like here, the textbook example is taking the natural logarithm of this proportion, but there are like slight modifications. So if you actually go ahead and calculate by hand these values from these formulas that I gave you, you might slightly get different values. So if you want to know what this one's doing, you can actually go ahead and read the documentation to make sure that it's actually doing the thing that you're aiming to do. So now, for this new document, this English document is interesting. I'm going to use the TF-IDF to compute the scores. And then computing the scores, I will be showing you the feature vector computed through these IDF scores. So here, instead of plugging in the number of the times the word appears, we're just going to plug in the TF-IDF score of that specific word. So here we can see that like this is the feature vector of the sentence, and each of the values correspond to the TF-IDF score computed in the previous section. So let's see like what are the advantages and the disadvantages of TF-IDF. Again, it's a pretty straightforward approach to implement. There's no like sophistication or complexity in it. Specifically, this is valuable if we don't have a lot of computation resources available on premises. And again, it captures semantic similarity between two documents because we can compare those, compare like any n-dimensional vector and find a similarity measurement. And it's very commonly used. So in practice, like many existing NLP models are actually using TF-IDF in them because it's fairly promising for like some of the NLP tasks. But the drawbacks are, like the first one is the curse of dimensionality, which is a famous term in the deep learning. So as we can expect here, as we increase the size of the vocabulary, the dimension of the feature vector is just going to explode. And still we're missing out on the semantic relationship between individual words. So still we're blind on that side. And again, as we can see, the vector can be sparse. It can put us into a lot of troubles when we're doing matrix computation. And if you have a new word, so if I say this, cat is interesting. It's not going to like present this sentence through its word representation in a very like, fair manner. So this doesn't actually hold a lot of information about this sentence because we didn't have it in our vocabulary. We didn't have the word cat in our vocabulary. So there's that. Now we saw some of the major classical examples of word representation models, and a common drawbacks of all of them was the fact that they were all, the feature vector that is computed through any of them is pretty sparse. So word embeddings are state-of-the-art models of computing word representation that would also tackle this limitation of sparse representation of different words. So what word embeddings are doing is actually trying to compute a dense representation. And let's see how they're actually doing that. So different words, if we can use them interchangeably, that means somehow they have a semantic relationship with each other. So take a look at this sentence that I took out from Wikipedia. So it's originally, the cat is a domestic species of small carnivorous mammals. So as we can see, we can really like interchangeably use dog. The dog is a wild species of small carnivorous mammal. Now, the sentence might not mean anything, but semantically it's plausible. So we can actually leverage this potential in linguistic information and try to improve our word representation to come up with a dense feature vector instead of a sparse. So let's see a famous word embedding model, which is word2vec. Now you might hear word2vec a lot in different research topics or different like articles because it's a widely used approach to compute word embeddings. So word2vec is not like a single model; it's actually a family of different architectures to learn word embeddings from large data sets. Particularly here, we're going to take a look at skipgrams. So the idea behind skipgram is that we have a training set, and we're going to like sweep through this training set, and particularly we're looking for pairs of context and target words. And I'm going to explain what I mean by that. So let's say we have this set: female domestic cats can have kittens from spring to late winter. So let's say the context word is cats. Now we define a window around this word, so we can see like plus minus m words here, right? I picked 2 words, and in this window of words, all of the words that appeared in this window are going to be associated as a target for this context word. So just by taking this portion out, we can build this set of pairs. So the context is going to be cats, and target is female, domestic, kittens. Now, what we really want to do is that we want to find a function or a mapping that would transfer your context to a set of potential target. In order to build up that model, we are going to leverage the neural network. So what are the inputs to this neural network? The inputs are going to be the one-hot representation of the context word. And the output on the other side is going to be the one-hot representation of the target word. So as you can see, we're basically trying to find this highly nonlinear function of mapping between context and target. I here briefly mentioned some of the maths behind this, but I'm not going to go through it. I'm just going to mention that like the loss function is this entropy loss. And if we minimize this loss function, simultaneously, we're going to maximize the probability of predicting the target word given the context word. So if we perfectly train this neural net or wec neural net skipgram on a large data set, we're going to have a perfect function that would map your context set of words to your target set of words. And through this, we can extract the embedding matrix that does this mapping. And this embedding matrix actually contains all the embeddings of the context words in your data set. So that's how we compute the skipgram word embedding from this neural net. Is there a question here?
Yeah, well, I don't have questions, but just to make sure that we don't lose the big picture here. So guys, we started off with a corpus. So going back to the example we just shared with you, we had a bunch of narratives that were labeled as spam and ham, and our end goal was to build a pipeline for classifying the new narratives as spam and ham. And we reached the part that we wanted to build some feature set. So far, Ali Reza talked about like different techniques to produce that feature set. So we looked at the bag of words, we talked about pros and cons, and also TF-IDF, and then we transitioned to the word2vec. So just to have that mindset that, hey, now we are at the position that we're going to translate like different narratives that can have different length, different structures. One can be a bunch of just, let's say, 5 words. One can be a long paragraph. But at the end of the day, we want to have like a bunch of features to later on use in classification or different ML approaches. So with that, just wanted to make sure that we all are on the same page. And if you want to get deeper in the nuts and bolts of these techniques and understand like better what's happening behind the scene from a mathematics perspective, you can spend more time and researching on this. But the application wise is that these are going to be fed later on into an analytics pipeline. Yep.
Yeah, that was an important point. Yeah, we shouldn't lose track of the big picture as we're focusing really deep on these acute details. So let's actually go ahead and use the skip graph model. In order to do that, I'm going to use the GenSim library. So let's load the first one. So here I'm actually using the common text built in the utilities of the GenSim library. And let's look at the common text corpus. So it's a fairly toy corpus, a little example of the different words in each document, the human interface computer. That's just the first document all the way through the last one. And the version of the word-to-vec model that I'm trying to fit on the common text data set has a size of 10, and the window size that I was talking about is set to be 5. And it has like other parameters that you can set a parameter of minimum count to disregard those words that appeared less than 1 time. And this is just like how many threads of like parallel computational resource you're going to use. It's not really important. So let's run this and let's see the feature vector of some of the words. So let's see the feature vector of human. So I'm going to print no, actually, here let's see similar words to. Sorry about that. Let's use this representation. So as I said, you can find similarities between words, like semantic similarities, with the dense representation. So let's pick human and try to find similar words to human in our corpus. So word is our word here. The human is similar to. And let's take our model and say most similar. To W, and we're gonna see the top. Oh my God, suggestions are killing me. The top N, I'm gonna set that to 2. Right, so here we're going to use the trained word-to-vec model on our little corpus to see the top 2 similar words to human. It must be string, okay. So I'm just going to have to change the type. Okay, so it's telling me that on this very small data set, human is similar to interface with a 61% probability, similar to epsilon, whatever that is, by 53%. So yeah, as we increase the size of our corpus, we'll get better results that makes more sense. Okay, so let's jump into another word embedding model that we're going to see actually some interesting results of it. This next one is GLOB, and it stands for Global Vector for Word Representation. The whole idea of GLOB model is built around the calculation of this matrix, which is called co-occurrence matrix. The co-occurrence matrix quantifies the number of times different words appeared, together at their adjacency. So you can actually do the window thing that I explained before and sweep the text with a window and compute how many times each word appeared in the context of different, in the target of different context words. And doing that, you can build up this co-occurrence matrix. And here we're going to use a neural net model that I just briefly mentioned the math, but I'm not going to go through it. But the idea of GloB model is that we're going to measure how related words are using this coherence matrix. So basically, we are making this assumption that if two words are appearing together a lot, that means they're somehow related. There are like different tricks to get it to work, like setting a weighting factor for the words that appear 0 times. I'm not going to go through it, but let's actually try this. So again, I'm using GenSim library, and here we're just going to use a GloB model that has been trained on Twitter data set. And this is just a very large corpus of just people tweeting stuff. So let's go ahead and run this out. It might take a while because it's going to like download that model, and this model has huge parameter sets. It's going to take a while. As we're waiting for this, just maybe shoot a message in the chat if you have any question.
I have a question on the word to vector module.
Yeah, sure.
So if you please go back to the word to vector example you showed us.
Oh, sure. Yeah. So is that this one?
Yes. In the example you said, what I understood is that you are trying to get similar words to human, or maybe I'm wrong, but
Exactly.
the result in interface
exactly.
and EPS, I don't understand how they relate to human.
Oh yeah. It might not be like really intuitive, and that is because I trained the word to vec model on this very little small data set here. Right? So I think I showed you the common text data set.
Yeah.
It's just this little data set, and you're not going to get much out of this like little information. So if you like train this on Twitter data, you might get better results. And actually, we're going to see that like in the GloB example.
Okay, so I mean, not more to the meaning of it, but I just wanted to understand how it found interface and EPS based on what. If you can explain that, it would be great.
Oh, sure. Yeah. So basically what we're doing here is that we are loading up a pre-trained model and kind of modulate it based on our data set. So this is just the model being stupid because the data set is stupid, right? Because the data set is just human. I mean, let's try it on human. Can you find the most similar word to human in this data set? Like, which one is most similar?
I would think computer.
It's hard to tell, right? Right. But apparently with this like limited data set, the model was not successful doing that. You probably need a larger corpus. And let's actually see that. That was a great question. So that, back to your point, that means you need huge data sets and large neural network to successfully train a word embedding model. And that's not actually practical for like many of us sitting at home with our like little laptops. That's why like most of the big corporations like Google, Facebook, perhaps Microsoft, they actually release pre-trained models that you can download and then pre-train, and they're pre-trained. You can actually download them and kind of train them on your data set. So this is not going to be an end-to-end training. So you're going to take on the training and then try to modulate it in a way that fit your data set perfectly. So that was a good point. So let's move on to this GloB model that has been trained on the Twitter data set. Now I mentioned, is this correct? Is this completed? Let me see. GloB model. Okay. Because it's freezing at like 70%. I mentioned multiple times that we can measure similarity between dense representation of different words in the vector space. Now we're going to actually see what I mean by that. One of the ways to measure the similarity between two vectors is the cosine similarity. And it's basically trying to, find the cosine of the angle between two vectors. So for instance, like these two vectors, they almost point in the same direction. And as we can see, like the cosine is like very close to 1. But these two are like perpendicular, so they're actually like irrelevant to each other, and the similarity here would shrink down to 0. Let's go ahead and build a function that would compute the similarity for us. I'm going to use the special of the SciPy library, and I'm going to use that to just calculate the cosine distance. So here, the similarity is going to be 1 minus 1 spatial distance cosine. Plot model of the first word. So the similarity is taking two vectors, the first vector and the second vector, and the glob model is calculating feature vector for both of them. And through this function, 1 minus the distance between those, we can get the similarity. Let's run this. All right, now if we call similarity, we're going to get the similarity between those two feature vectors. And there's a lot to play with here. Let's actually do some interesting examples here. So I'm going to define some of the words that we're going to use to, compare the similarities. Let's define two similar words. So the first similar word is going to be man and woman. And let's try to define a set of two different words. We're two different, and this is going to be like man and what is different than man, like umbrella. Okay, so now let's go ahead and call the similarity function of the feature vectors of these words. So in order to do that, I'm going to print, actually format this text so that we can plug in numbers, the similarity between so the similarity between W1S and W2S, that is going to be equal to, and let's call our function similarity W1S and W2S, right? So this is just going to spit out the cosine similarity. Let's do this. So what is the syntax error here? What? Oh, okay, I actually didn't. This. Should work out. What am I missing here? Double quotation here. I'm actually not going to need this one. Should be single quotation. Okay. This one. Okay. So the similarity between man and woman is 76%. So let's actually compare that to those two different words. So man and umbrella. I mean, one would guess those two things are pretty not similar. So similarity between man and woman is, oh, I actually forgot to change these. I was surprised by the result. What do you know? Man could be similar to umbrella. The similarity between man and woman is 76%, and the similarity between man and umbrella is 48%. So as we can see, the word-to-vec embedding is capturing this semantic relationship between those two things. And the word-to-vec actually doesn't stop here. Let's compare the relative relationship of different words with each other. So I'm just going to compare the similarity between large and larger and small and smaller. So if we just like try to picture this vector space, those two words in each set, they need to have like almost a similar difference vector. So in other words, what I'm saying is that similarity between large and larger needs to be like pretty much similar to the similarity between small and smaller. Let's see, okay. So as we can see, similarity large and larger is 86%. Similarity between small and smaller is 86%. Now, let's take a step back here and actually think about what we're doing with this model. As I mentioned, this model is trained on Twitter data, but let's think about whether tweets are, you know, a fair source of information for training AI models. So let's assume I'm going to use this word-to-vec model to make a decision for the society, like for admitting people to university, for getting the job to them or not, or to review the job applications, things like that, putting people in prison. And my basis information is coming from society tweets, and that could contain anything. It could be biased towards a specific group of people, or specific gender, specific minority, and it could contain tweets from anyone, from me, from Trump, from anyone that you can imagine. Let's see an example of how the word-to-vec model and word representation and word embedding can be biased. All right, so let's actually try to measure the similarity between a person and a career. So here I'm gonna set, no, this is not right, career. So let's say I'm gonna be a doctor, right? And in my job application, I wrote down my name. So let's pick a set of male names. And along with it, let's also pick some set of like female names. So John. John wants to be a doctor. Carl. Stephen. My friend here, Ashton. Even myself. And I'm just trying to like pick names from different demographics. And say Asian. Okay, so those are the main names that will cover a wide range of different demographics. And let's actually pick some corresponding female names. So let's say Rose want to be a doctor. Emma. Lily. Kylie. Yasamin. Zahra. And Shania. Okay. So what do we have here? We have a career and we have a set of names. And we got these job applications, and I'm just gonna plug in their CV inside our model and decide who to accept and who to not accept. So for the name in male names, let's actually go ahead and print the similarity. Right, so the similarity between these two. I'm just gonna put a title on it, print. Right, and so this time it's going to be the similarity between career and a name. So let's do the same thing for female words. This time it's going to be on female names. Now, right, apparently your name shouldn't be an indicator of whether you're similar to a career or not, but see some results. So the similarity of John and the career doctor is 80%, while the similarity of myself and a doctor is 4%. So as you can see, for different demographics, you'll get different similarities. So almost like Muhammad and Sean, there's no way they can get the doctor career, including myself. That That's because our name are not represented in the data set. I mean, who's going to tweet my name? That'll probably be me only. And let's actually compare different genders. So here we can also see the same trend from Rose to Shania, almost a similar trend, the similar trend for, for more, I would say for like certain demographics, you would see larger similarities. And actually, if you average out the female names, it's going to be lower than the male names. So that's the famous example of, doctor, and you just have this pre-assumption that the doctor is someone who's male, right? So if you just like say doctor, you assume John more likely than like Emma. So as we can see, if we use this word embedding in our model, that's going to be used in somewhere to make decisions for the society. This is actually going to cause a lot of problems and a lot of bias towards a certain group of people, certain gender, or certain demographic, any type of like different minorities. This is an active topic in research, and if you just look up articles under, let's see, what's the name of it? Okay, fairness in AI. If you look that up, there are actually multiple conferences, and people are actually actively working on the topic that now that we're actually going to use AI to make decisions for people, and that decision might affect the life of a lot of people. Let's try to make those algorithms as fair as possible. All right. Let's take 5 here. I think we can use a couple of minutes, and then we can regroup after 5 minutes.
Yep, sounds good.
Is it not really late for you? Like, what is the time there now?
I'm sorry?
2:30 or something? No, is it like isn't it too late for you guys there? Like, what is the time there now?
Oh, it was a hack, but not actually. No, it's like 1:30 in the morning.
Wow. So it's like a hackathon.
Yeah, exactly.
But with a lot of talking instead of coding, right? Usually in hackathon.
Right. Yeah.
But it's really interesting because I am also like starting to look at NLP, and you are starting from the basics. So that's really good. So even for people who are new to this, I think it's really useful for them. But at the same time, you are talking about the relevance of it in real use cases. So even for people who are working on it already, it's useful. So I think the mix of both is really great.
Great. Yeah, I actually mentioned a couple of resources at the end of this notebook that if you're just interested in a specific topic that you want to follow into a little bit more depth, you can actually follow those links. There are great courses from Stanford, great articles in the OpenAI website, and things like that I think I mentioned at the end.
Great.
Right, let's get rolling so that we'll have enough time to actually do the conclusion at the end. I'm going to briefly gloss over different types of language models. And in this section, first, I'm going to introduce some basic probabilistic language models. And at the end, we're going to see some examples of more state-of-the-art recurrent neural network. And at the end, we're going to see how to use transformer models, because everybody's talking about transformer models. Okay, so what is a language model? A language model is nothing but a conditional probability. So if you're familiar with the whole theory side of probability, and like not even too much deep probability, just like the definition of probability, a language model is trying to find the probability of the next set of words, right? So as I'm speaking up until this point, a language model is trying to predict the next set of words or the next word that's going to come out of my mouth. So that's the goal. So let's formulate this. A language model is probability of that sentence, which is going to be a joint probability of individual words in it. And a related task is to predict the probability of a given word, given its history. So given the history of all previous words, let's actually try to predict the probability of this word. And you can actually use this to predict the next words in a text. Let me see. We're actually going to skip some of these. But let's see this example. So if you're familiar with the chain rule in the probability, you know that the probability of this sequence is in a chained fashion is the probability of the first word, probability of the second word given its history, which is the first word, probability of the third word given its history, which is the two words all the way to the last word. But there is a theorem by Markov, a pretty famous theorem. Markov assumption is that if you want to compute the conditional probability of a word given its full history, you can actually kind of truncate that history. So there is a set of k immediate history that's going to be a sufficient statistic to describe the same probability. So I don't really need to look all the way back to the very beginning of the document. So maybe just looking at the previous 5 words will suffice your computations. Okay, so building on top of this idea, a unigram model is just saying that I don't want to look at the history. So the probability of a sequence of words is just the probability of each word. The bigram is looking at the closest adjacent word as its history. So basically in the bigram, we're making the assumption that the last word is a sufficient statistic to describe the probability of the word at this time step. And we can actually, build on top of this idea and go all the way to engrams. So if we want to formulate engrams, engram is saying that the probability of the sequence is the product of the probabilities of each word given the past and histories, just the past. Okay. So theory aside, let's jump into an example. And in this one, I'm just going to use the natural language toolkit that Ashton introduced. I'm loading the engrams. Let's define a function that would, extract engrams from a sentence. So in order to do that, I'm going to use engrams. I'm going to use the model, and then let's take the NLTK and tokenize. Oh, I should need to word tokenize our sequence. So the input is sequence and engram, number of past history that you want to keep in your memory. So engrams of the tokenized sequence, and so this will give us the engram. I could actually read the documentation to familiarize yourself with different parameters in this. Okay, so we downloaded and set this model. Now we have this sentence by Aristotle: the whole is more than the sum of its part. And ironically, we're going to use the engram model to break down this into engrams. So let's say I want to see engrams of 1, 2, so I want to see unigrams, bigrams, trigrams, and 4grams. So for I in n, I'm going to print the number of engrams plus grams, and then let's go ahead and call this function engram generator. of our sequence, which is the sentence, and N. Okay. N-gram is not defined. What am I missing? Local area reference before assignment. Okay. So this is one part. Generator. Around that part. Where is one of my function? Okay, so it doesn't return the output. That's not it. Okay, see, and grams out. Let's see. Oh, you know what? I actually made a mistake here. So let's, like, this is going to spit out the n-grams themselves. We need to stick them together to actually build the n-grams. So we need to return, like, using a space. Let's go ahead and join the grams for grams in this n-gram output that we computed here. So this is just, you know, a fancier way to visualize this in a more, you know, sentence-like way. N-grams not defined. Can you spot my where I'm missing here? Sequence. Let's see. Okay, let's actually read the error. Okay, I don't know what happened, but so here we're going to see the n-grams of this sentence. The whole is more than the sum of its part. So the unigram is just, you know, individual words. The bigram is a window of 2 words sliding through the sentence all the way to the foregram that is just a set of 4 words. Now you can just, if you have a corpus, you can break it down this way and compute the probability of each gram, right? So you can count the number of times who is more appeared in your whole corpus, and that way you can assign a probability to that n-gram. All right, so that was n-gram. N-gram is not the best way to do a language modeling, obviously, because you're truncating the history, and sometimes the history matters. Like you need to have a full history of what happened before in order to be able to predict the future. So that's one of the major drawbacks of the n-grams. And if you have the bar sentences, this is going to fail. And that's how we're going to get to the idea of how recurrent neural networks were introduced. So basically, the idea of RNN is to overcome this drawback of the n-gram and try to find a way to define memory for your sequence, for your model in the sequence. RNNs are actually very promising in different NLP tasks, and like most of these state-of-the-art models are built on top of some type of RNN. So let's take a look at a very basic example of a recurrent neural network. So this is a recurrent neural network which is being repeated at each time step. If you look at the elements in this cell, there is an input element at each time step, and there is an output element, and there is this A signal that is like passing through all the time steps. And this signal is actually representing memory. So you're injecting the signal, hoping that in a way we can somehow introduce memory and keep this memory throughout the time steps. I also mentioned like some of the math behind what's going on here. So basically, if you're familiar with how neural nets are formalized. This is just basically the same thing. We're trying to build a nonlinear function of the input and the signal and all that. Okay, so there are different variations of the RNNs, which is important to know. And actually, Ashton's example later on is going to focus on one of them. So the first one is a one-to-one mapping. And if you look at this, this is just a basic neural network, which is taking an input and spitting out an output. So this is just a neural net. The next one is one-to-many. So you have one input, and that's going to generate a sequence of output. One example of this variation of RNNs is like music generation models. You're just going to give it an input, and it's going to like output how many sequence of the future. The other one is many-to-one, which is going to be the example that Ashton is going to be going through later. So it's taking like a series of sequence, and it's just spitting out a single value. It could be like binary or any type of like different classes. So this is useful specifically in the case of sentiment classification. If you want to get a single output, class output out of a sequence of different inputs. Many-to-many case is you have a sequence and you map it to a different sequence, and it's useful for NER or named entity recognition. Now, if I want to quickly explain what named entity recognition is, I just go back here. So the task of named entity recognition is that the named entity recognition model is going to look at this text, and it's going to see prompt. So it's going to tag it as a person. Fans, perhaps people. President, that's a title. So you see, it's just it has a preset set of entities that's going to correspond to the words in our data set. So that's the named entity thing. And then many-to-many, as Ashton mentioned before, it's very used in machine translation. And actually, if you dig into the source code of Google Translate, you're going to see something like this. Now, the first basic RNN cell that we can build is that we're actually taking this similar basic RNN, but this time we're using tanh, the hyperbolic tangent, as the activation function. And this is one of the earliest type of recurrent neural network that you can find in the literature. Now, moving on to a more sophisticated example that I'm probably sure you've heard a lot about it, LSTM. This is there's a big hype around LSTMs. So let's just actually walk through the processes behind an LSTM. So LSTMs are pretty old. They're not like something new. They were introduced back in 1990s, but obviously because computation resources were limited back in those days, no one used them. And now we have like all these GPU kind of computation resources, and we can train LSTMs. So the idea behind LSTM cell is that an LSTM has memory in it, but it also has long-term memory. So it learns how to associate its output with inputs in the past, and it kind of learns the lag between the correspondence of input and output. It's pretty much like how we semantically understand the meaning of things. Let's see. So this is how it looks like. It has a pretty sophisticated computation inside each cells. But I will just gloss over what are different steps in this cell. So there are 3 gates in each LSTM cell, and each gate has a specific task assigned to it. The first one is a forgetting gate. Next one is the input gate, and the last one is the output gate. The main idea behind an LSTM is that let's have a signal that we add to or remove to. And this actually means let's have a signal, a memory that we learn things, we memorize things in it, and then we forget stuff out of it. And that signal is the cell state signal that passes through all of the LSTM cells. And the second signal is the hidden state, which is equal to the output at each time step. So these 2 signals always pass through an LSTM sequence. So as I said, the first sequence is the forget gate. Here we decide what to forget and how much to forget. And after this, we have the input gate. the input gate decides what to remember, and in order to come up with a candidate of what to remember, it also actually computes the updates for the state cells. So basically what it's trying to do is that it's gonna add stuff to the state cell. So this is passing along here, and the input gate is gonna attach some memory to it, while the forget gate is just gonna, you know, draw some of the information in the state cell signal. Next, we're gonna update the cell states by the approach that I just mentioned. So we're just gonna take out stuff by the output of the forget gate and add stuff using the output of the input gate. And just in the last gate, we're gonna have this output gate. The output gate is actually doing the job of computing the output of this cell using the memory signal, the input, and the hidden state from the last time step. Okay, this was just, you know, a hand-wavy explanation of how LSTM works, but if you're interested, you can just, you know, there are millions of resources online that goes through the formulation of it. LSTM looks good and promising, but they obviously, like anything else, there's some drawbacks to it. The main drawback of LSTM is that due to its sophisticated formulation, there is a danger of not being able to train it due to the phenomenon of vanishing gradient. So as you're doing the backpropagation to train your neural network parameters, you might reach to a point that you basically have no ability to update your parameters because the gradients that you were using to update the parameters actually are, you know, very small to zero. So there's that. So practically, as I said, like ironically, the LSTMs were introduced to overcome the limitation of memory, but like honestly, they're not doing a great job at doing that. They do keep some memory, but it's not like really long lasting. So that was LSTM. Now, what is a deep recurrent neural network? The answer is pretty straightforward. If you just, you know, stack many layers of RNN cells, you're going to get a deep recurrent neural network. As I said, there was a big hype around transformer models. If you follow the news, you might have probably heard GPT-3 model that has been released just, you know, a couple of months ago. And previously last year, the OpenAI company also released GPT-2. So let's actually try to, you know, have a big picture of what a transformer model is. The transformer model is nothing but, you know, a deep recurrent neural network, which is basically on top of LSTM cells, but they have an additional component, which is attention. Now, attention mechanism is what's making transformers really great, and that's, I'm not going to go through how, like, mathematically how it's going to do that, but let's actually try to get an intuition of what an attention is. So let's say we want to do sequence-to-sequence machine translation, and we have "How are you?" and we're going to translate that into this. I think it's Korean. So we're going to translate that into the Korean version of it. Now, as you might know, different languages have different grammars, and they might put different words in different places, right? So "How are you?" in Korean might sound something like "You are how." That could be like one way. And the attention mechanism is basically telling each LSTM cell to pay attention to you know, to kind of modulate the attention of that cell to different inputs. So for instance, the attention corresponding to this output cell is telling that, hey, look, you got to pay more attention to this than that, this step. And then, you know, you got different attentions at different outputs. So that's the main idea, behind the idea of, you know, attention mechanism. And there's a paper famously named by "Attention is All You Need," and it's pretty straightforward if you want to read it and get more familiar with the mechanism of the attention. Lastly, let's play around with GPT-2. Just, you know, don't be scared of these big names like GPT-2 transformers. They are pretty straightforward to use and load if you just load the library. The GPT stands for Generative Pre-trained Transformer, GPT. and they were developed by the OpenAI group. And like these people are incredible. I highly recommend that you check out their website. They do all kinds of things, and the good thing is that mostly their work is open source, so that anyone can have access. And that's why they call themselves OpenAI. There are different variations of GPT-2 based on the parameter size. And basically, the GPT-2 is making use of this luxury of large data sets of 8 million web pages are used to train a GPT-2 model. And not anyone has access to resources to do this type of learning. But luckily for us, we can just import them. So let's pip install PyTorch transformers. And the good thing about Google Colab is that it already has like PyTorch and anything in it, so you don't really need to install a lot of packages. So I'm going to import PyTorch from Google Colab, and let's import GPT-2 tokenizer and GPT-2 multi-head attention model. So it has like multiple attentions. So let's do that. And here I'm loading the tokenizer from a pre-trained GPT-2 model. Next, I will be loading the model itself. So I'm loading a GPT-2 multi-head attention model from pre-trained. It's going to take a while because it's a huge model with lots of parameters. They've done incredible things with GPT models, right? You can, lately there's been an article in the Guardian news website that had been generated by GPT-3. Like there's a whole article that has been written by this model. Okay, so here's how our model looks like. So these are like different layers, different portion of the GPT-2 structure. You can look through if you're interested. Like there is a multi-layer perceptron, dropouts, or residual connections, all sorts of things. Let's move to actually try to use this. So here I'm going to use this to predict the next word in sequence. So I'm loading the tokenizer. I have my text. I tokenize it, and then using the loaded model, I will be trying to predict the next word. So first, let's tokenize it. So the tokens are this, and this is according to the convention behind tokenizing words in the GPT-2 model. And then let's try to use the output of the model and try to predict the next word. So here I set my text to artificial intelligence aims to predict the, and then I'm using the output that has the maximum probability assigned to it. So let's see what is the most likely word after artificial intelligence aims to predict the future, which makes sense. And actually, this is what Google is using when you're looking up stuff, and it actually suggests you things to if you want to look at this. Okay, and if we build on top of this, we can actually generate feature sequences. So in order to do that, I'm going to have my sequence, predict the next word, take the new sequence, predict its next word, and continue doing this until I have a full sequence. So in this section, I'm going to use 150 words after this sentence intelligence is most often studied in humans, but has also been observed in both. Let's see, what are the predictions? It's going to take a while because basically we're calling the model function 150 times over and over again. Come on. I stop this right now, I'll probably get some output up to this point, but I just, let it roll. And the thing about Google Colab is that if you use it more, it's going to get slower because you have, a limited access to its computational resources. So if you, use it a lot, it's going to get slower for you. But, okay. All right. See the predicted text, the predicted text. So intelligence is most often studied in humans, but also has been observed in both animals and humans. A study published in the journal Nature Communications found that the brain of a human autism was more sensitive to the presence of chemical codes. So you see, like, if you step back and largely look at this text, this is a plausible text. It might not like specifically be accurate or scientifically be accurate, but it looks like someone, actually a person, has generated these texts. Like the study was conducted in a laboratory at the University of California, San Diego. So yeah, I suggest that you play around with this transformer model. You can actually load that. No, I'm actually not sure if they released the third generation publicly. I think that has been commercially released, but you can definitely play around with the GPT-2 model, and it's freely available. I mainly got my stuff in these references. So if you're interested in any part of it, just follow these links. There is a great course by Andrew Ng at the Coursera, and like different stuff that I just mentioned here. This is also a great blog by someone who works at the OpenAI. So yeah, that was it. With that being said, I just hand it over to Ashton.
Yep. No. Thank you, Elireza. Before we transition, just let's take a quick pause. We had a lot of material to cover in this session.
Yeah, sorry about that.
Anything from the group? All right. So, okay, cool. So before we move to the last section of this workshop, I just wanted to, excuse me, just put some stress on some of the materials that Elireza just shared with us. So initially, he talked about some continuation of more advanced methodologies on creating features, and later on that can be fed into some of the both supervised and unsupervised machine learning models. And then we transition to RNNs, LSTMs, and some more sophisticated algorithms. And it's really key to understand the level of applicability of these techniques. So one thing that I deal with on my day job on a daily basis is working with clients that they have heard some of these terms. And when you talk about like different solutioning for real life problems, they ask you, hey, for this problem, why didn't you use LSTM? So, and it's really key to be able to distinguish like for which problems you should go after these techniques, meaning that really depends on the size of the data, the sophistication of the problem you want to solve. And usually this RNN-based models should be the last resort, not the first one. So in real life problems, for most organizations, they don't have the computational power to handle some of these sophisticated techniques. But for you, if you're a part of an organization, or you want to start up your own company, or if you want to go after the research area behind these techniques, it really matters if you know the nuts and bolts behind any of these methodologies. And if you want to use them in practice, you should know the pros and cons of any of them. And it's something that is very popular in data analytics community, is always start from small and simple models. For example, in machine learning, if you can solve a problem with regression, there's no point to transition to more sophisticated models. And just because your clients or even you have heard the terms like deep learning, it doesn't mean that the first thing that you should apply is a deep learning model. So please have that in mind. It really matters because it really affects the quality of your work in practice. And also when it comes to productionalization of your solution, you just saw that even on a small data set, it takes some time for a model to run and produce results, and it takes much longer time to evaluate and make sure that the results are relevant and is applicable to the client, the user. So companies like Google, they invested a lot of money for implementation and also for validation of these techniques. So it's important for all of us to have that grasp as well. One other thing that I would like to underscore is the mathematical aspects of in some of the techniques that we just saw. And if for some of you things that were not quite clear and you need more time to have a deeper dive session on these, please remember that, for example, on RNNs, you will find courses online that they spend like 8 weeks or 12 weeks only on that. And here in this very brief workshop, we only had like so much time to introduce the concept to you. So it's important for a person that's getting familiar with natural language processing to understand that, hey, there was a journey for folks starting to extract useful information from textual data, from starting very, very simple, like the way that we saw in our example, to break the sentence in multiple words, to remove stop words, clean it up, extract some very basic features, all the way to we are seeing on the other side of the spectrum of like text generation, transformers, all that, like attention modeling. So it's important to have that understanding, like what changed, like how folks went after more sophisticated algorithms, and that was along with having access to more computational power. So as to Ali Reza's earlier point, like LSTM or RNN models, they were around even in 90s, but nobody cared about them, just like most deep learning models, because they were not feasible to apply until GPUs become available. They got cheaper. Even Google, they recently released their TPUs to basically accelerate running these models. So things became feasible recently. And that's why we're seeing that NLP is trending really strongly these days. So just wanted to close this section with that in mind. So if you're interested to get deeper into the mathematical part, by all means, please leverage some of the resources that Ali Reza added to his page earlier. And please feel free to Google some of these topics. And right after this workshop, if you wanted to circle back with either of us with questions, please feel free to do so. So any questions, anything that you want to raise before we transition to the last topic?
I actually push the solution. Sorry, I actually push the solutions to like whatever I coded up to the repository, so you can also get that if you didn't get a chance to follow up the codes.
Yep, fantastic. Anything else from folks?
So you talked about all these techniques for English language, and there itself we can see there are a lot of challenges and things to learn. So how easy is it to do NLP for any foreign languages? Do these packages and tools still apply?
Iris, do you want to take that?
Yep, sure. So like some of these packages, I mean, they've initially built around English language, like the whole idea of tokenization and things like that. Like most of the libraries, they have English in them, but they are like over and over, they've started to work on other languages as well. And there are actually research articles that, that try to do this transition from the English language tools that are built inside of these libraries to use them in a way that would apply to other languages. Like I've seen papers for Arabic language, and also I think I've seen Chinese. So it's building up slowly. I wouldn't say it's an easy task. Like if you want to do if you wanted to have stop words in like my language Farsi, it's actually not built into natural language toolkit. So you need to somehow either build it yourself or try to, you know, find it in a way. So it wouldn't be readily available, but this is a topic that's being worked on.
Great, because since this event is also about SDGs, right? We see that especially in the developing world context, there are like a lot of information that is unstructured and in text format, but most of the cases, the language is not English, and that is one of the biggest challenges. So you explaining that there is a lot of research happening here actually makes a lot of sense, and I think many of the people who are watching this also might be interested to look into the other languages and research aspects in how to do NLP in other languages. So thanks.
Sure. Yeah.
All right, awesome. Yep, great discussion. Any other questions? All right, if there's no other question, let's quickly transition to the first notebook that we started the conversation with. I would like to spend maybe 10-15 minutes on completing that notebook, and then some other important general topics around NLP. And then I would love to open the floor for any Q&A. And we can wrap up the session in 25 minutes or so. So let me quickly share my screen, and again, please let me know if you're able to see now.
Yeah, we can see the screen.
Okay, fantastic. So if you recall, I opened up the conversation on the notebook by saying that, hey, we're gonna read some data and we're gonna pre-process data, and we saw a couple of examples of cleaning up the text using by removing the stop words, tokenizing a sentence, and stemming and limitization. Just a couple of very simple approaches to cleaning up the data. And one quick thing that I wanted to stress over is, for example, for tokenizing a sentence, I showed you how you can leverage a regular expression, regex, to look at the distances. But again, in the couple of examples that Alireza shared, there was an NLTK word tokenizer, or there were even more sophisticated approaches to do that. So it's important to just be aware of these tools. So you don't have to go after the most sophisticated one, to my earlier point, and you don't need to go after maybe the simplistic version, which is regex, that only searches for the empty space to break up the sentence to tokens. So again, in your career, you're gonna run into situations working with folks with different levels of experience in NLP. And it's important to have that grasp that all these techniques exist. Maybe you're not an expert in all of it. Maybe you don't know the mechanics behind, let's say, LSTM or RNN, but it's important to understand that, hey, these techniques exist, and what are the pros and cons for each technique. So when it comes to actually solutioning on real life and also productionalization of any of these solutions, you can tell that, hey, for this type of problem, maybe I can start with something simple. If it's work, fantastic. If not, I can move to the next level and make things more sophisticated. So we started by reading the data and pre-processing it by making it a little more with less noise, if you will, after removing the stop words, and a very simplistic approach to tokenizing the data. And one example of stemming, we use Porter Stemmer and also WordNet Limitizer. And I mentioned that we're going to talk about feature engineering, and Alireza talked about some cool, more conventional, and also a little more sophisticated approaches for producing features of a corpus of data. So we can think about like very, again, simple approaches to produce those features. Just think about a length of a narrative. That can be a feature. So in your corpus, you have a sentence which only has 3-4 words, and you also have a narrative which is like a paragraph. So if you think about it, maybe even intuitively, we can assign a probability if shorter sentences have a higher chance of being a spam, or maybe not. So, or think about the number of punctuations in a sentence. We can also normalize that. Like, how about the ratio of the number of punctuations divided by the length of that sentence? And when I say sentence, it can be the entire narrative, the entire comment that we have in our data. These are clever ways to produce these features. So things, they don't have to be only math-based. So in some real life applications of NLP, most of the time that people spend, it's not really on the modeling part, but they spend a lot of time in coming up meaningful features. So they think about like features very simplistic, just like what I said, like the length of the narrative or the ratio of punctuations to the length. And also they add up some additional features, let's say from TF IDF or word2vec or whatever else that is out there. So after you have that feature set, then you can transition to the next. For example, the example that I'm going to share with you is just user those features to train a machine learning model, and then evaluate that model. Just see if you like it, if you don't like it, if you want to go back and change any of this. So if you want to just work with a subset of data, if you want to change your approach in pre-processing the data, or your feature engineering strategy, all of these things are fair game. So nothing is set on stone. So with that, let me go back to what we had. So what we had was a very simple data frame where we read the data and we produce a data frame with labels as spam and ham, and also the narratives associated to those labels. So for the interest of time, I'm gonna show you how we can just tie things together and build a very simple form of analytics pipeline to address NLP problems. So in the first cell, nothing fancy here. Again, we can import NLTK, pandas, regex, and also in the example that Ali Reza shared with us, he also used TF-IDF vectorizer, which is resident in scikit-learn, feature extraction, text. This is really handy and very easy to use. Also, what I wanted to show you is just import the package string. And the cool thing about this one is this is a collection of all those special characters which we'd like to remove. So if you recall that regex example, there was what basically a creative way to get rid of those, but we don't have to do that. So there is a package to address that exactly. So if you recall, first of all, let me run this. Okay, so if you recall, we activated all this stuff works in English, but Parvati, to your question, so here you have a good range of languages to specify. So NLTK is very rich to address questions across many different languages. So here we just specify the stop words for English, and also we just produce an instance of a Porter stammer, if you will. So, all right. Here we read the data, it is tab limited, we assign the labels, all right. And let's take a quick look at the data head. We have the labels here and we have the body of text. All right, now this is the part that I just mentioned to you. So first of all, for every, okay, I produce a function for adding features, adding those simplistic features. So before you take a look at this part, take a look at this part. So here we can just produce the length of the text. So for every narrative, we calculate the length and we remove all of the spaces, of the empty spaces that we don't care about. And also here, we produce an example of a function where you can define, hey, for every character, make sure that it's not a punctuation. And after that, you just count them. Like, what is the actual length of the narrative after you remove the punctuations? And also you divide that by the whatever is remaining out of the length of text minus the empty spaces. So see, by doing this creative ways, I just produced 2 new features to my data set. The first one is the length of the body, and the second one is the ratio of punctuations to the length. Maybe they seem too simplistic, but that's okay. Another phase up to the work is just to cleaning up the text. So I produced one function. Oh, by the way, let me run this one. And let's take a look at the data head really quick. So see, for the first one, which is a spam, the length is 128 and the punctuation percentage is 4.7. So 4.7% of the characters resident in this narrative is punctuations. So maybe it's something that tells us a useful information about a narrative being spam. Maybe not, but it's something. We can look into it later. Okay, so another function for cleaning up a text. So let's see what it does. So when it receives a text, the first thing it does is make sure that the words within that sentence, they're not a part of the punctuations. And also it makes sure that everything is lowercase, nothing is uppercase. Then it tokenizes with the most simplistic way that you can tokenize a text. So what you can imagine is a list of words which are tokens. And after that, it checks that every token is not a part of the list of stop words, meaning that we're getting rid of the stop words in a sentence. And lastly, we're stemming the word. So once you receive a narrative, you apply all these operations on that. You make sure that the words are not punctuations, everything is lowercase, then you tokenize, then you make sure that it's not a stop word, then you stem it. All right. Another step is just applying that TF-IDF vectorizer. Remember, we already imported TF-IDF vectorizer here, so we can directly apply it here. So we produce an instance of it, then we apply TF-IDF fit transform, and you apply it on the body of the data. So let's do that really quick. It takes a little bit of time, but after that, you see that, hey, we already produced 2 features, body length and punctuation percentage. And here we added all of those features that were produced using TF-IDF. Now, I have my feature set. This is the phase that I call feature engineering. I had a bunch of narratives. They had different length, different structures. Going back to here, see, there were some that there are capital letters. We had a bunch where there are some special characters. I took care of all of these instances and make them to some extent comparable. And after that, I produced a feature set like this. Now it is ready to be fed into machine learning algorithms. Now, the machine learning algorithm that I wanted to use is random forest, which is very popular. So I read it from scikit-learn, and also some other very, very handy features of scikit-learn like k-fold and cross-value score. So nothing fancy here. I just read them and also just build a random forest classifier. I make sure that my k-fold, the number of splits is 5. And then I just feed the X features, which is this guy. And also the labels, are the labels in my data, and run them. Okay, so takes a little bit of time to run, but shouldn't be that long. So let's give it some time. And by the way, yeah, the scoring is the accuracy of the model, but later on we can see more granular measures for performance management and having a more granular level look at them. All right, while it's loading and we're waiting for data, oh, by the way, there you are. So yeah, we had 5 folds of data, and look at the accuracies, and they seem pretty decent, but that's okay. Like 96%, 95%, so they seem okay. But let's take a look at precision and recall F-score. So, and also when we look at K-fold, we know that yes, random forest classifier is doing its job. It's a good model here. But actually, let's apply it on one break of the data when we just assign 80% of the points in training and keep 20% for testing. So I broke the data to X-train, X-test, Y-train, Y-test, and I trained the classifier, random forest classifier, on one set, and let's run it on that particular split on the data, on the train and test. And see, the precision is 100%, the recall is 50%, the accuracy is 93%. And these are pretty decent measures, which is okay. I mean, they're not fantastic, but these are a good start. Meaning that when I come here and look at these numbers, it just tells me a good sign, like the feature set that we produce to a very, in large, it's doing its job. And the classifier random forest it's pretty decent. So if I want to make things even better, then I move to a new feature set. So how about using word-to-vec or other more sophisticated approaches to look at the text? So this is one example of transitioning from very raw data all the way to evaluate the performance of the model. So if we want to do more sophisticated approaches, we have a great range of tools in our back pocket to go after. So if you want to go and use RNN-based models like LSTMs or gated recurrent units or other techniques out there for your project, for your job, by all means, we can do that. But the key things to remember here is, let me go back to the slides really quick and just remember this. At the end of the day, we should have this mentality in mind to produce a product or a process, and that's what is needed in the marketplace. So one other thought, actually 2 other thoughts to leave you by. So Ali Reza talked about different language models, like producing dictionaries and like all of those techniques. Like when we talked about like clusters like glove, usually those neural networks, they are trained based off the data which is out there in social media and the internet, like in Twitter or Facebook, whatever is out there. But when it comes to industry-based problems, for example, you want to build a neural network only on healthcare. You want to create a chatbot for patients and on a very specific field, let's say for folks which are already diagnosed by diabetes, and you want to build a chatbot to answer their questions. It's really important that your data dictionary has lots and lots of medical terms within that specific area. So I highly suggest that you look at IBM Watson, which they have produced industry-specific data dictionaries. And they have done a fantastic job for when it comes to, let's say, finance or manufacturing or agriculture or biology or these days, there is a huge research with this pandemic situation to addressing, like building chatbots to answer folks' questions on COVID-19 diagnoses. It's important to have that glossary of relevant words. So that's one comment that I wanted to leave you by. And the last thing I wanted to tell you is, okay, so if you recall the prediction or forecasting the election results in the first round and second term of Obama's election, it was very easy. So folks like Nate Silver, they were easily capable of reading and interpreting the textual data resident on social media to forecast people's voting results, and they were capable of forecasting the election results even per state at US. But things were quite different in last election when Trump and Hillary Clinton, they were competing for presidency. And the key outcome of that analytics space, that NLP solutioning for that election, was that people say things on social media, but they behave differently. So that was a big learning for the analytics community, to not only rely on textual data, but look at other behavioral data as well. So textual data is very, very important part of a system's attributes. So if you want to, for example, learn about somebody's behavior, you have to look at different features. So because of that, companies like Amazon or Netflix or Google or Apple of the world, they invest a lot of money to analyze the data of their products out there, but also tie that to other behavioral models of people, like what you search on Google, what you buy on Amazon, what you watch on Netflix, how you interact with your Google Map. So the combination of these behavioral attributes, in addition to what you say, can tell them what is your next behavior, what would be the best product to suggest. So, okay, let me leave you with that thought. So understanding that nuts and bolts of NLP techniques is crucially important. But remember, that's the beginning, not the end of the story. So we are almost at time, and I would love to leave some time for the group here to share if you have any questions, any comments for us. Unless I'm sure me and others of you had a fantastic time in this workshop, just sharing some of the fundamental and also cutting edge technologies in NLP with you. And as I said, this is just the beginning of our interaction. If you have any other question by the end of this workshop, it doesn't really mean that our relationship is going to end. Please make sure that you feel free to reach out if you have any thoughts, any questions, if you needed any advice in terms of your career or research. Please feel free to email either of us, and we're more than happy to get back to you as soon as we can. But if there are no other talks, Parvati, I can hand it over to you.